In this video, I'd like to cover a few examples using definite integration. So first I have the integral from 0 to 2 pi of cosine x dx. The first step in evaluating this integral is first just checking that this function is continuous from 0 to 2 pi. And from our knowledge of trigonometric functions, we know that cosine x is. So then we can proceed. So first we find the antiderivative. And you should recall that the antiderivative of cosine x is sine x. And note that I'm omitting the plus c since it will cancel when we do this definite integration. And then I write this bar indicating that I'm about to plug in 2 pi. And now I simply plug in, and we have sine of 2 pi minus sine 0. And from the unit circle we know that both of these values are 0. But does this make sense? Can the area under a curve be 0? It can. Note that for cosine, if I'm to draw a quick sketch from 0 to 2 pi, the graph looks something like this, where 0 is here and 2 pi is here. Note that for cosine, when we integrate from 0 to 2 pi, we are calculating all of these three regions. This one, and this one. And we're summing these three together. And as mentioned in the previous video, areas that are above the x-axis are called positive, and areas below the x-axis are called negative. And for cosine, these two areas are equal to this area. So the net area under this curve is actually 0. So 0 is a possible answer for a definite integral. Let's try the next example. X cubed minus x from negative 2 to 2. Well, we know that x cubed minus x is a simple polynomial, so it's definitely continuous. So then we find the antiderivative. Using the power rule, we know that this is x to the fourth over 4 minus x squared over 2. And we will evaluate from negative 2 to 2. Now note that since both of these exponents are even numbers, that negative 2 squared, or negative 2 to the fourth, will equal 2 to the fourth. So this is actually 0. Once again, since we'll have 2 to the fourth minus negative 2 to the fourth and minus 2 squared over 2 plus negative 2 squared over 2. And finally we have the integral from 0 to 5 of dx over x minus 3. For this case, note that we have a discontinuity at x equals 3. We have an infinite discontinuity at x equals 3. And therefore, we cannot apply the fundamental theorem of calculus to evaluate this integral. And let's just visualize this, why this makes sense. For the graph 1 over x minus 3, at x minus 3, so I'll graph it here, we will have on the left side as it approaches 3, we'll have it approaching negative infinity, and here it will approach positive infinity. So we'll be unable to calculate this area under the curve, which is why it makes sense.